Now, we'll be discussing Lesson 1, Direct and Indirect Proof. Okay, let's define first what is mathematical proof. A mathematical proof is an argument which convinces other people that something is true. In principle, we try to prove things beyond reasonable doubt at all. Okay, in dealing with integers, one sees a pattern in a series of statements, and usually a conjecture or a guess follows. So if a conjecture has been proven, we call it a theorem. A theorem is a statement that can be proved by using previously learned concepts and principles and/or by logical reasoning. Usually, a theorem is stated in the form if P, then Q, where P is the hypothesis and Q is the conclusion. Okay. In mathematics, we study statements or sentences which are either true or false, but not both. For example, 4 and 6 are both integers, and consider the following statements. We have statement 1. 4 is an even integer. Statement 2, 6 is an odd integer. Statement 1 is true and statement 2 is false. We will use letters P and Q to denote such statements. Properties of integers may be proven directly or indirectly. This lesson discusses the methods by which the properties are proven. There is no exact proof that can be used to prove any property. Okay, first we discuss the direct proof. So direct proof is a method of proof showing that if the implication is true, the conclusion must be true. So assume that the proposition is true, then derive some facts to prove that the proposition is also true. And then we use the form if P, then Q. So suppose P is true, then we derive some facts to prove that Q is also true. Okay. As an example, using direct proof, prove that if x is an odd integer, then x minus 3 is even. So in this example, x is an odd integer is called our hypothesis, and we denote that with P. Also, x minus 3 is even is our conclusion, and we denote that with letter Q. If x is an odd integer, then x minus 3 is even. So we will start with this proposition P, and then we will derive some facts to prove that x minus 3 or our Q is even or true. So suppose x is an odd integer, then it follows that x is equal to 2n plus 1 and n is an element of z. So, we start with x is equal to 2n plus 1, and then to derive x minus 3, we subtract 3 to both sides of the equation. So, it will become x minus 3 is equal to 2n plus 1 minus 3 by addition property of equality. And then, manipulating this, we have x minus 3 is equal to 2n minus 2. Then we factor 2 to determine whether the right side of this equation is an even or an odd integer. So we determine the common monomial factor, which is 2 times n minus 1. And then let k be equal to n minus 1, where k is any integer. So we could replace n minus 1 with k such that x minus 3 is equal to 2k. Hence, we could deduce that x minus 3 is even. So, this is the way we use direct proof in proving this proposition. So, let's have another example. If p is an even integer, then p squared is also even. So, just the same, we start with the hypothesis. Suppose p is an even integer, then using the notation for even integers, we have p is equal to 2n, where n is an element of the integer. So we start with p is equal to 2n, and then to derive p squared, we square both sides of the equation. So p squared is equal to 2n quantity squared. So it will result to 4n squared. Now to determine whether this 4n squared is odd or even, then we factor out 2. so that 4n squared will become 2 times 2n squared. And then we let another variable k to represent 2n squared, where k is an element of z. And then replacing 2n squared with k, we have p squared is equal to 2k. And now, we concluded that p squared is also an even integer. Now we proceed to the indirect proof. Another technique of proof is to show something's true by showing that it cannot be false. Assume that the proposition is false and then derive some contradiction to known facts to prove that the proposition cannot be false. So there are two methods of indirect proof. One is the proof of the contrapositive and the other is proof by contradiction. So if we use proof of the contrapositive, then if we have a statement if P, then Q, denoted by this symbol, its contrapositive statement is not Q to not P. We are interchanging the places of P and Q and we are negating the statement. So this symbol denotes that it's the negation. So if it's stated positively, then the contrapositive must be stated negatively. While for the proof by contradiction, to prove a sentence P by contradiction, we assume not P and derive a statement that is known to be false. So, meaning to say, if we have a positive hypothesis, we will negate that statement and then we derive a statement that is known to be false. So, if P then Q, then we assume that P and not Q. So, the caret here denotes that it's and. It's a conjunction. Using indirect proof, prove that if x is an odd integer, then x minus 3 is even. So here, our hypothesis will be x is an odd integer. So here, our hypothesis is x is an odd integer, and our conclusion is x minus 3 is even. So the contrapositive of the above statement is, if x minus 3 is an odd integer, then x is even. We negate this and make this as our hypothesis, then negate our original hypothesis and make it as our conclusion. I hope you understand the way we convert any statement into its contrapositive. While the contradiction of the above statement, if x is an odd, then we denote some facts to derive that Q is negative. So, here originally, x minus 3 is even. So, in our contradiction statement, we have x minus 3 is also odd. Okay, so let's have an example. Proof of the contrapositive. Let's show the proof for the above example using the proof of the contrapositive. So, using the contrapositive statement of this original statement, we will start with the hypothesis. So, suppose x minus 3 is odd, then we have x minus 3 equals to n plus 1, where n is an element of z. Okay. To derive x, we have to add 3 to both sides of the equation. So, we have x minus 3 plus 3 is equal to 2n plus 1 plus 3. And then, it follows that x is equal to 2n plus 4. And then, we have to factor out 2 to determine whether x is even or odd. So, getting the common monomial of this binomial, we have 2 times n plus 2. And then, we let k to be equal to n plus 2, where k is an element of the integer, such that we have x is equal to 2k. So, here, it means that x is even. Therefore, the above statement is proven to be true using the proof of the contrapositive. For the proof by contradiction of the above statement, let's convert first the given statement into its contradiction statement. So, if x is an odd integer and and x minus 3 is also odd. So that's the contradiction statement. And we will start with the first proposition. So suppose x is an odd integer, then x is equal to 2n plus 1. So we will start with x is equal to 2n plus 1. And then to derive x minus 3, all we have to do is to subtract 3 to both sides of the equation, giving us x minus 3 is equal to 2n plus 1 minus 3. And then by algebraic manipulation, we have x minus 3 is equal to 2n minus 2. And then we have to factor out 2 to determine whether the right side of the equation is even or an odd number. So let k be equal to n minus 1, where k is an element of the integer, then we have x minus 3 is equal to 2k. So hence, x minus 3 is even, but since in our contradiction statement it's odd, then we have a contradiction. So this, or the original statement, is true using proof by contradiction. So in proof by contradiction and proof by contrapositive, we convert first the given statement into its contradiction and contrapositive statement to prove that the original statement can never be false. So let's have another example. Using indirect proof, prove that if p squared is an even integer, then p is also even. So p squared is an even integer is our hypothesis, and p is also even is our conclusion. For the contrapositive of the above statement, if p is an odd integer, then p squared is also odd. While for the contradiction of the above statement, if p squared is an even integer and p is odd. So proof of the contrapositive, if p squared is an even integer, then p is also even. So its contrapositive statement is, if p is an odd integer, then p squared is also odd. So we will start again with the hypothesis. So suppose p is odd, then we have p is equal to 2n plus 1, where n is an element of the integer. So we'll start with p equals to n plus 1, and then to derive p squared, we have to square both sides of the equation, such that we'll have p squared is equal to 2n plus 1 quantity square. And then expanding the square of a binomial leads us to 4n squared plus 4n plus 1. Factoring out 4n squared plus 4n, we'll have 2 times 2n squared plus 2n. But since 1 cannot be factored out, then it will remain unchanged. Okay. So we let k to be equal to 2n squared plus 2n, where k is an element of the integer. Then p squared is equal to 2k plus 1. Therefore, p squared is odd. So that's all for this session. I hope that you understand the difference between the use of direct and indirect proof in proving properties of real numbers. I will entertain questions in our next meeting. So see you next time. Bye-bye!